Hello, everyone. We're jumping into Unit 3. So that means that you've completed your Unit 2 test. And just a reminder, you can do test corrections or a retake on every single exam, but you only have a week to get those done. So I need those done by October 9th. Now, test corrections, you just open up the test, and for the ones that you got wrong, you, on a separate document, explain to me the correct answer, and then you email me that document, or you could just write it all in an email. You'll get a third of your missing points back. Now, at that point, when I reply to that email, I'll give you the code for the retake if you choose to retake the exam. So that's how that works. Okay? All right, let's jump into our next unit. So we have day 1, learning target 1. I can define force and use free body diagrams to identify the force acting on an object. Okay? So first thing, when something is speeding up, slowing down, or changing directions, then we say that it has acceleration. And force and acceleration are directly linked to one another. So if I look at this box that's sitting on a table, how can we cause the box to move? Well, we could apply a force. We could start pushing it. Okay? And so what are all the forces acting on the system, on the box? Well, we have an applied force here. Okay? An applied force, which just means it's being pushed by something. Okay? But there's also other forces acting on the box. Gravity is acting on the box, so we have force due to gravity. Okay? And then we have a third force acting on the box. There's a reason why the box is not just falling through the table, and that's because the table's pushing back up on it, and we call that a normal force. Okay? And so here in a moment, we'll go into more detail about all these, but if we were going to take a free body diagram, we'd say, for this box, and I'm just going to represent it with a dot, we have force due to gravity, we have normal force, and then to the right, we have an applied force. All right. Now, contact forces and field forces. Contact forces are when something is in contact with the actual object and it is supplying that force. So just like how our hand is directly on the box when we push it, that's a contact force. Or the table is directly touching the box, and so that's why the normal force is also a contact force. Now, field forces are different. They're when the force is acting, but the object isn't directly in contact. And so gravity is a field force. Like if I take this pen and it's not touching the earth, but when I drop it, there's still, and there is right now, gravity acting on it, even though the earth is not in direct contact with it. So gravity is a field force. Another big field force is magnetic field forces. Okay, so a force, a push or a pull that causes a change in motion. And so all these pushes and these pulls will give you a net force, which will cause the object to accelerate. Now, acceleration is a change in velocity. Now that could be the speed or the direction because velocity is a vector. Okay, so we have, oh, this is kind of for the next one. We have a ball attached to a string, and so the string is in contact with it, so that'd be a contact force. And then we have these point charges here. So like this positive charge is repelled by that positive charge, and it's repelled by that positive charge, but it's attracted to this one. And even though they're not directly touching each other, that magnetic field force is still there. Okay? Now we have a big list different types of forces. Okay, so one type of force that you'll run into is a friction force. This is a contact force, and it's when we have two surfaces, maybe it's the surface of an object and then the surface of the ground or whatever, and they're moving past one another, there's friction there. Okay, we have a spring force. If you compress a spring, it's exerting a force back on you. Tension, like when you pull a string, like if there's a box attached to a string, you pull that string, you are applying tension to the string, and that tension moves the box. Thrust, like with a rocket, okay, that's a force that gets an object accelerating. Then we have weight, which is the force due to gravity. And so you'll hear me call this force due to gravity more often than I call it weight, but they're the same thing, okay? And then normal force is a contact force, and it's when an object is leaning up against a surface, whether it's sitting on the surface or leaned up against it, and that surface isn't applying a force back on the object. So like when I press and push my hand down on the table is pushing back up on my hand. That's why my hand doesn't just go through the table. And so that is called normal force. Okay, let's go into some more detail about free body diagrams. Free body diagrams is a way that we represent the forces acting on an object. So force is a vector as well. It both has a direction and a magnitude. And so we can use the arrows to show us the direction, and then the length of the arrow will tell us the magnitude. Now, if all of the forces acting on an object are canceling each other out, like do you see how this force here has the same magnitude as that one, but in the opposite direction? So these two cancel each other out. And when all the forces cancel each other out, that means the overall net force of everything is 0. And that's when an object is in equilibrium. When these forces, their overall addition of all of them is not 0, then we have an acceleration occurring. So back to this object, you see how this force here is greater than that one, and so it cancels with a small portion of this, but there's still an overall net force going to the right. And so in the x direction for this object, it's in dynamic. It is going to be accelerating. Now, an important thing to recognize, do not include forces exerted by the object. So like if I'm doing the free body diagram of my hand pressed against the table, I'm not including the force of my hand pushing against the table, but I am going to include all the forces acting on my hand. So I would include the force of the table pushing back on my hand. But we're going to do lots of examples. All right, so here's how you should go about doing a free body diagram. First, we're going to create a model, a pictorial model. We're going to identify all the forces, and then we're going to label those forces as arrows on the object. Okay, so we have a ball suspended by a string. So we have a ball being suspended by a string. Let's just say it's being suspended, so either someone's holding it or it's like attached to the ceiling. Okay. And when I look at this, the object is the ball. So that's what I want to do my free body diagram for. Okay. So the force is acting on the ball. When I look at this picture, well, I know that the force due to gravity is acting on the ball. And I know that tension is acting on the ball. Okay. And so those are the two forces that I've identified. So the last part of this, I'm going to make a dot that represents the ball. And then I'm going to have my force due to gravity is headed down towards the earth. And then tension, according to this picture, is pulling it straight back up. To be force of tension. Now, when a ball is just suspended from a string, it's not it's not moving, right? So its velocity is constant, and it's a constant zero velocity. So we know that it is in equilibrium, that these net forces, everything that's acting on the object has to cancel out. And so that's why I drew my tension force to have the same magnitude or length as my gravitational force, because they should cancel each other out since the object isn't moving. Okay, let me see how much time we have. Okay, let's do one more. A raindrop falls freely from a gray cloud, and we're going to ignore air resistance. Okay, so we have our cloud and we have our little raindrop there. And when I look at this for the object, which is the raindrop, so not the cloud, we have the force due to gravity acting on it, and we don't have air resistance pushing it back up. And that would be it. There's no other forces acting on this object. So that's what the free body diagram would look like. I have a dot that represents the object, and then it has a force due to gravity. So its net force is down this direction. There's nothing to cancel that out. So we would call this dynamic, okay? And because it's dynamic, it has an acceleration. It's accelerating towards the earth. All right, when we come back for the next video, we'll start with talking about these 4 examples.